This is a demonstration of our new pie cut tube routing feature, which we're going to use for exhaust headers, specifically equal length headers, and also other piping and conduits that need to be routed in tight spaces using bend radius that are smaller than a manual or CNC tube bender. To start off, we're going to get the software that will run these demos. It's available at armaautomotive.com. You go to Tools and then scroll down to Arma CAD CAM software. Click on the link. Alternately, you can scroll to the bottom and there's a link in the footer for Arma Design Studio. So to download the software, click on the links for your platform. If you have Windows, we have a Windows build. If not, we have a Java build. We will have a Mac OS version coming soon. If you click on these and download them, you can get the application running. This is recorded with ADS version 1.2.37, and there is likely changes to be made. When first launching ADS, there is a blank canvas, and there may be, if you have worked in the software before, some saved files in the top header so that you can quickly load them again. Otherwise, you can open saved files here, and right now all of the features are available, but in the future there will be plans that you can purchase a license for. Just orientation on the software. This view, it displays the contents of the scene, and you can view one or four different perspectives so that you can, this is handy if you're moving in one direction, but you want to see what's happening in another. This tool here, I will just add a object so that you can see. This pan tool lets you select objects, and use on the Mac, you can hold the Option command to rotate, Command key to pan, and just clicking will drag the will drag an object around. So the pan tool will also two fingers will let you pan. So Command will let you rotate around the objects that's selected. Command will let you pan the view, and then without any keys, clicking will let you drag the object around. So we have some primitive object types that you can add to the scene. There's a cube, sphere, cylinder. You can edit the properties, meshing, and line, polyline tools, curves. You can adjust the settings. So in the right-hand side of the screen, you can see objects that are added to the scene in the list here. So if I click on the selection tool, I can grab them, move them around. The scroll wheel will zoom in and out. Option will let you rotate. Command will let you pan. Double click will let you pan. So the center mouse button will let you pan. And today, so in the right-hand side, these icons up here are for Boolean operations. So if I see view from the front, I can make a shape, and then I want to subtract. It will create a subtraction folder, and then I can create another object, and it will hide the this is a work in progress, but you can see how you can construct Boolean shapes. These are good for 3D printing if you want to quickly build something together without dimensional constraints. Okay, so today we're looking at pie cut tube routing. So ADS has features for tube notching and bending with this tool here. This is an arc tube. So an arc tube has properties that define a physical metal piece of tube. And the way that it works is you click on the tool to activate it, and then on the screen you click points where you want segment lengths of a tube. So if I click here, double click to release it, it draws it as a blue line. I can look around. Now, because this tube has no thickness, it will just show up as a line. But if I choose from this list of material here, a piece of steel, 1.5-inch outer diameter, 1/8 wall thickness, I can see now that it pops into place. It's got outer diameter, inner wall. So this example tube has a bend radius of 4.5-inch, which is a property associated with the particular type of tube. So each die, bending die, is going to have a particular bend radius, which gives you this geometry along the curvature. So the tube will have a wall thickness and then the bend diameter. Some tubes may have multiple bend radii, but you're probably just going to have one. This is an example tube bend. I'm going to set the material to 1 3/4 inch. So it will show up here. And this will actually put tube notching. Well, I want ends. So outer ends are good. So it's going to add in the tube object, it's going to add these two end caps, and they tell the machine that fabricates this how to cut the length of material out. But we want a pie cut, and because this is a pie cut, we can change the bend radius to one that's not supported by a bending die. So I'm going to say 4 inches, which gives us a much tighter bend radius, and we want we want to fabricate this tube with pie cuts. So it changes the color so that you can tell the difference between what materials in your project file are to be cut with a notcher and a bender, or to be cut with a notcher and then fit together with pie cuts. So you can see some markings on this tube. If I click on the tube, I can see that there are these pie cut shapes. I can click on one and then see what it's made out of. The machine will cut this profile out of the tube. You may be wondering why it looks like this. So the physical tube will result in this curved shape. But while the tube is rendered in the curved shape, there's no way to display the notches that will be applied to the tube in a way that makes sense. So what's happened here is this tube, when it's fabricated, this section and this section and this section are unrolled into a straight line, and they're cut from a single piece of metal. So when they're unrolled, you can see this circle, this dot right here. This is where the points that define the tube are located. So when the tube is fabricated, if I click on CAM for computer-aided manufacturing, I have some options here. One is for plate material, arc tube for notching. So this is a CNC tube notcher, a plasma cutter. Will cut a tube out of material based on the designs in your file. And the arc tube bend G code is for a CNC tube bender that we offer as a service or as a product. So because we're cutting pie cut parts, we're not going to use um, the G code for bending. And because the tube knows that it has these pie cuts in it, it won't generate the bending G code because we don't need it. So if I if I select the object, I can rotate it a little bit more easily. And that is the principle of how we model in the software the um, tubing that we want to fabricate. So it's most likely that you're going to be doing CAD design in other CAD software. We also use Fusion 360 and SolidWorks. So there are importing options that you can use to export a mesh object from another CAD software and import it into ADS, and then convert it into an arc tube, add your intersections, notches, and features, and then manufacture it. I believe it will be get arc tube from mesh. So if you import a uh, mesh object, an OBJ or STL, export it from Fusion 360 or SolidWorks, you can import it into ADS, into your project. You can select the object in question and then choose this option menu, and it will, like this illustration shows, take a mesh object and then convert it to our representation of the arc tube, which can be have the operations done on it to do the intersections, coped intersections, so that tubes can fit together. This outer and inner are just for perpendicular. Adding the ends basically tells the machine where to cut the ends, which is important. You can add tabs to the coping intersections so that the tabs and slots in the corresponding tube so that the pieces fit together and you don't need as many jigging infrastructure when you're building your parts. And then there are tools for managing lots of intersections. So if you have tube intersections with 3 or more parts, it's going to generate multiple notch profiles and you'll need to combine them. Bend angle markers are basically pin pricks with the tube notcher that mark the start and end location of the bends for a CNC tube bender. And this we use for validating that when we bend a part, we have the tube lined up accurately in the bender, and that we can verify that each part is bent so that the bend profile marks the start and end. We know that the part that we made is actually going to fit. We can rotate the part just in case you need to change after the CAD model, and then you're going to take it to the hardware. You need to put it in the machine a different way. You can rotate it. This is probably an old feature from marking old mesh-based tubes. This is going to be replaced by the new arc tube feature. And dash was a experimental feature. So we have some cases where we bend tubes in the CNC tube bender that are really tight to the end. So this tube bender has a limited, a minimum amount of space that's required before and after a bend. And if you have a part with a cut that's right up to the edge of the bend, you can't put it in the bender because the bender won't be able to grab it. So this idea was that we would perforate a tube. You could put it in the bender and bend it, and then you could cut the part after because it's partially perforated. So this is the tool, this is the new tool that we'll be using in this video, notched pie cuts. The idea is that you can take a CAD model design of an exhaust or a coolant line or any kind of metal piping that you want to route in software. You can do the design and you can export a G code which tells the tube notcher how to cut it from each tube in one piece, and it will cut multiple slots, and then the slots will allow the tube to basically fold like a slinky, bend to shape, and then you can weld back together the gapping in between each of the pie cuts and reconstruct a complete tube with your shape. And you don't have to take lots and lots of pie cut pieces and assemble them together. You can do it in CAD, cut the whole thing in on the machine, and then put it together and fit it and weld it. This application, we have a F-136 block, kind of. This is from a Ferrari, but I have a Maserati 4.7 liter V8, and it has a cross-plane crankshaft, so it will have a even odd firing order, so the engine sound will be distinctive. And in my vehicle, I want 180-degree equal length headers so that the exhaust tone sounds more uniform or smooth. So in order to do that, I'm going to build equal length headers with pie cuts. And in order to design this set of headers, there are lots of considerations and it will take quite a bit of effort. So we have this tool. The file is not organized, so pardon the mess, but we have this generative design feature which will basically optimize routing for tubing for equal length, short length, and to avoid collisions. So I'll fire this guy up and just give a quick explanation of what we're looking at. This dialog on the right has properties for the routing operation. Now, this routing is just optimizing the center path. It's not going to change the ends of each of the tubes. So we have 8 exhaust headers, and they're all connected to the header, and then on the other end, the collector at the exhaust. So this software is basically going to evaluate the performance or the value of this configuration based on a few different things. How many collisions, so the tubes can collide with other tubes can collide with the object, with the scene, and then there can be a value that indicates if they are equal length and if they are long. So it will try to move the exhaust headers so that it will reduce the length. This property here, change, will adjust the amount of motion in each iteration. It's going to make a modification. If the modification is better, it'll keep it and keep modifying off that. If it's not better, then it will revert back. So we have a few checkbox options here. Equal length will optimize as it's running for equal length, and reduce length will basically try to move it so that the tubes use as few as minimum amount of length as possible. Parallel is a sliding scale that will optimize an aesthetic property so that the tubes will tend to try to, lengths will try to follow the same parallel lines, or if not that, then perpendicular lines. And we'll see if that actually has any effect. We'll experiment with that. So I'm going to start. It's going to take some time to start up. And you can see motion in the tubing here. And you can see an original fitness score, which is how the value of the orientation of this tubing when I started, it was laid out so that each cylinder number will run in sequence around this collector. So the design from the endpoints is defined, and then I just want the computer to figure out how to route them given the space that it has. So later on, I'll put in the model for the chassis. So there are constraints. There's going to be fuel tanks and then tubes running for the chassis. And later on, I can run this and optimize for that shape. So you can see the amount of time that has elapsed. The current fitness value is alternating between two. So the best value and then a modification. IPS is iterations per second, and this is quite computationally intensive because it's comparing basically intersections, checking to see if these tubes are colliding with a pretty complex scene. And then it reports the current evaluation based on the number of collisions. You'll notice this over time. As soon as it gets rid of the collisions, it will this number will drop off. And then it shows the number of accepted changes and rejected changes. So a rejected change means it's made a modification and it's worse than we had. So we'd throw it away and try again from the best. So this tool will use the CPU, as many cores as you have. This is a MacBook Pro with 10 cores, and I'm getting just under 1 iteration per second. So I'll pause it for now. One of the other attributes, padding, is a sliding scale that lets you give a zone around the tube. And this serves as a few functions. One is it allows you to define how much space you want between the tubes. When you're assembling these, at some point you're going to want to weld some of them and then assemble them and weld others. So you may want to give yourself some room to get a welding tip in. This will let you dial it back to basically nothing so that the tubes can touch, or give it some good padding. The second function that padding does when doing this iterative function is this function is not, this function can get into cases where it can't get itself out of. So a tube could be wrapped around another tube around a corner, and it doesn't know that it has to expand in order to get around the corner. So padding, when things get bunched up, padding allows it to basically get itself out of a corner if it paints itself into one. You can see the number of collisions, which is the primary factor in evaluation, is dropping significantly. So I will stop this. And I'm just going to demonstrate some other functions of the equal length routing. I have two tubes here, and it's intersecting in a couple of places. And we also want to make sure that when we have it route, that it still maintains a valid shape. Okay, I'm going to run it again. You can see collisions have quickly dropped to 0. It's no longer colliding there and there. And then we can look at equality. Point 2, what it's going to do, because the cube is in the way, it wants to make this tube longer. So it's going to have to eventually shift in order to get some extra length. Point 1, it's dropping. You can see it's working its way. The top tube, I suspect, will stay in the same spot at the top because it wants to, it's longer, so it wants to stay there. Yeah, and you can see the bottom tube is inching its way forward. So the idea of this tool is not that you click a button and you get an optimized design right away. It will run, it will use the resources of the computer to your advantage. The longer that you leave it, ideally, the better of a design you get. So you can be doing your design work, your fabrication work, and then the resources, compute resources that you have can be working in the background, optimizing your products. Okay, I'll do another demo. This one I always think is fun because we have two interlocking tubes, and so what it's going to want to do is try to make them equal length. Let's remove that. We want it to reduce the length, and we're going to demonstrate the padding value. So if I click start here, you can see both of them are going to try to um, bring themselves together, but they can't because they are in each other's way. So they are anchored at the ends, and they can't come any closer because they collide with each other. So I'm just going to adjust the padding. This is usually default. You can see the property. They're maintaining a space between the tubes, or I can crank it way up, and then we'll just watch and see what happens. Yeah, that's quite a big distance. So you've got the flexibility to optimize. And because this is a small tube, you can see that it is making quick work. This is another example. We have a collision here and a collision here. So we don't want equal length. Let's just see what this thing does here. There's a collision here and a collision here. You can see the two tubes go in there. So we've got 122 value score, or 100, now under 100 collisions. Now the collisions are measured in polygons. So these structures are actually made up of polygons. So it gives us a very progressive scoring. When a tube slightly intersects with another, it's going to collide with one or two or three or 100 polygons, giving us an indication of small change can be better or worse, and that's exactly what we want in order to measure the performance. So you can just see these tubes twisted around each other. They're objects to interact with, and this tool is part of the generative design feature in the software. So the use case for this is going to be you scan, 3D scan, or import an object of the application that you want to design tubing for. You define the endpoints, so the start and stop points, and you basically run a draft version of the tubing where you think it could go roughly, and then you let the machine run, and it's going to experiment with a whole bunch of different avenues trying to optimize for the criteria that you're looking for. So it may take an hour, or depending on the compute available, it may take more or less, but it's meant to use the resources, compute resources that you have available in order to get you a better design. I'll just do another couple of features on tubing, pie cut tubing, and some of the features that you can use in the software. One of the options you can see here, I have a section of tube, and then I have a section of pie cut tube. Tubes are replicated using a mirror plane tool. So in a lot of cases where I am designing a tube frame chassis or some kind of application that's symmetrical, I don't want to have to replicate any of the design. So I can instead select an object, select this mirror plane tool, define it by 2 points, and it will basically split, replicate, or copy the object across an plane on the x axis. So if I move this object here, you can see that it brings it close together. This tube is replicated by this. So in addition to replicating, a mirror plane can also replicate objects that are um, single, so replicate from one side to another. So I have this tube here. I'm going to just give it a shape just so that you can see it. And then inside, I'm going to define, instead of vertical, I'm going to go left to right, and I'm going to span the gap between the center point. And this, like, it looks like a roll hoop, for example. I'll just name it. And then under it, I can see this mirror plane object is inside, and it's located in the point that I want to replicate. So I'm going to double click on this object so that I can edit it. And it's already replicated it. So you can see if I change an object on the left, it's going to replicate it across the right. If I move this point here, it's moving this point here. If I click on this point here, it's actually going to select this one. So it functionally will let you only modify one side. So if I click that one, I'm shrinking it, and then this window lets you edit the object. When I'm happy with it, I'm just going to click OK. It'll bring the changes back to this side. That's just an example of how you can create, define this shape. It will replicate it across. We can fabricate this part, and I can be sure that I won't accidentally forget to change something in one side and then have a part that doesn't fit and invalid, and I'd have to throw it away. But let's just look at these tubes here. I'm going to I'm going to want ends because in order for them to be cut, they need ends. Tube notching, I want ends. Then in the tube, it's going to add them here and here. And if I double click on this shape here, I can see the 3 points that define this pie cut. And I'm just going to look at it from the front. That must be a leftover object. And you can see, let's make some changes. Let's make it a shallower bend. So now we get fewer pie cuts. This guy is a laggard. You can see this selection option if a scene has way too many elements and you're having trouble clicking on the object that you want, like in this case here. I can just click on it from the list. This is possible options. So in this case here, let's reduce the bend angle, reduces the length of the arc, the number of bends. So now we're going to get 4. Oh, I see. Okay. This is buggy. It's a work in progress, but at least you can still get by. It's replicated a new end just because the geometry is different. This is very much a work in progress. You can see that the replicated colors are slightly different so that you can see that that's a bug. You can see which objects are primary and which are replicated. So now let's just take as an example, we want to make this. This is our part. This is what we want to make. So I'm going to, when I'm happy with this, I'm going to save, and then I'm going to go to cam, and I'm going to export tube notch G-code. So these tubes have a few properties that we need to set, and these attributes, this 360-degree angle in inches, defines when the machine chuck that holds the tube has a motor that rotates it. So the torch cuts from the top, and the motor is going to rotate the tube around, passing by the tip of the torch. And the motor is going to move a certain length, linear length, that will result in the tube rotating 360 degrees. So each machine that fabricates this, if you have your own tube cutter, plasma tube cutter, your machine will have its own length that the motor needs to move in order for the tube to rotate 360 degrees. So our machine right now is 5.5 inches. The feed rate is, feed rate basically defines how fast the tube moves and the torch moves over the metal while it's cutting. The fast feed rate is when it's not cutting, it's moving from one cut feature to another cut feature. It can move faster. M4, M5 enable, disable are specific to the G-code control software. So our notcher uses Mach 3 and Mach 4, and you can modify that here so that you can keep the G code to work on other machines. Continuous mode is a new method for cutting G code, and we've noticed continuous mode is a better quality than previously. So I'll just explain the difference. If continuous mode will cut each feature from start to finish and then move to the next feature and do the same. So I'll show you the G code that results. When you disable continuous mode, it basically doesn't roll the tube more than 360 degrees. So it will start a feature, and if it gets to the end of a 360-degree line, then it will stop, rotate the tube back 360 degrees, and then start again. So this will create artifacts and is really not a good way to go. Continuous mode is definitely the best option. Debug markup is really just for debugging. It's going to add markup to basically show on the screen how it's interpreting the geometry. And you would not want to do this unless something very, very wrong is happening. Stock length, CNC capacity length, and fixture scrap length are all relating to managing volume. So when you have a project with lots of pieces, you're going to have an inventory of metal that's going to come at a certain length. If it's DOM or crew tubing, it's going to come in lengths of between 20 and 24 feet. And our machine can cut up to 12 feet long, and each machine is going to be able to cut a different length. And when you fixture a tube into the notcher, into the cutter, it requires a chuck with teeth and a certain number of inches that the torch can't cut because there's nothing to hold onto the tube. So there's going to be some waste for each fitment. So when you generate the G code, it's going to generate a G code file for each part, and it's also going to generate a G code file with all of the parts in a project. And the reason for doing this is it optimizes which parts should be put together to fit on a tube to minimize the amount of scrap waste. So as soon as you start manufacturing, the scrap waste is going to become an important consideration very quickly. So when prototyping parts, it's great to just get a G code file, send it over to the machine, cut it off of a piece of scrap length, look at it, weld it, test it, and make sure that it's fine. But as soon as you're doing manufacturing, it's really good to have to be able to put in the length of material that you're buying, the length that the machine can support, and then it will decide how to cut the lengths of tube so that they fit in the machine, but then also in which order that they pack is basically a nesting function. So we're going to, for this project file, our tube pipe cuts, we're going to generate G code. It's going to tell us that it succeeded, and then I'm going to go look at the G code and show you what it looks like. So I'm just going to use a web-based G code viewer. In the project folder, the ADS file, Arma Design Studio file, it'll generate a folder with subfolders for each of the relating pieces. So tube nesting is going to have G code for all of the nested parts for manufacturing. PDF, if you're following, tube notching is a G code for each part, and we can also run the tube notch PDF and tube bend PDF, so we can just see what they look like. Bends, arc tube. So you can see if you don't have a CNC tube bender and you're bending a part, you can print these files off and get all of the instructions. So it tells you what the part file is, when it was generated, the details of the material, the compensated bend angle, bend radius, which expands. After bending, gives you the dimensions on the length. While you're bending, it tells you rotation for orientation, and then the bend angles to bend on your manual or CNC bender. But today we're looking at the tube nut and the G code. So this was the product that we were looking at. So I'm just going to drag it into the G code viewer, and it's going to look like this. So we're looking at it from the top, and this is the first, this is the end, and then it's going to cut these pie cuts, and this is the other end here. So this is the shape. Let's look at it from this side here. The order isn't correct because I didn't run that function, but you can see this is what it would cut. This is what the G code looks like. So we've got information about the file, the part, the date, the material thickness to use, the total length that we'll need, and then just some debugging information. So because it's made up of multiple segments, they're in triplets here. So the first segment, straight segment, bent, bent, straight segment, and then because the ends, there's nothing connected to them, they are 0. So that is a quick demonstration of how to design, cut, route, and export G code for tubing and tubing with bends made by pie cuts. There is a lot more to projects that use tubing, pie cuts, notching, but this is just a introduction. One other thing I think is actually really important, I will just show, is intersections. So I'm gonna make this tube here 1 3/4. Let's make it a little bigger. Front. Um, I have a tube, and this is a very common case. I want to notch it. This can be done with pie cuts as well. So these two tubes, basically they intersect with each other because they collide in the same space. So I'm going to go to Tools, Tube Notching, Angled Tube Intersection. So, okay, well, it kind of ruined that one. This is beta software, so let's just go in, delete those points, and now what we're going to have in this tube here, this tube is a notch profile that corresponds with the intersection of this other tube here. And we can add tabs and slots to that later, but that's just a very common example of something that we do with all of our parts. If they connect with something, it's going to be coped to another tube or another part, and then we're going to want that cut in the part. And if we're cutting this with a CNC tube bender, a notcher, and then a bender, we're going to probably use this tool right here, which is a bend marker. So if I click on this, it's going to add bend marker, and you can see they're just a little pinhole scoring the notcher will make on the tube, and these allow you to align, position the tube in the CNC tube bender or manual tube bender so that you know that the tube is loaded in the correct orientation and the correct location along the tube so that the part that you bend is correct. And these geometry are take into account bend radius, radial growth. So if you were to cut this part, this profile might be a minuscule amount different, but this point and this point is what you will get in physical material. What you draw is what you get. We've had good luck with bending so far. I'll just show you one of the projects that we're working on is this Jeep front bumper. So this product has tubes that are about 6 feet long. That this one has 6 bends, this one has 4 bends, and they are all fitting into tabs and slots. And the parts that we get are to a millimeter, exactly what we want. You can see the notch profile here. You can see the tabs, and then a slot, and having 6 bends and then have it come, parts fit together is exactly what we wanted. So that's an example of what we can do with arc tubes. This is pie cut queued up on the tube notcher. We've got the program ready here. 1 foot on each end with a 90-degree bend cut using pie cuts. Here is an 065 mild steel tube just for testing. Exhaust we would make with stainless steel, but this is just a test to check that the pie cut angles are correct and that the pie piece fits together. Let's go. Cutting off the end. Now we detach the tube. We'll let that cool. And we'll fit it up and see how it goes. Here's the test cut after without being bent. So this is an experiment. This is a 90-degree bend with a 4-inch bend radius. And I'm gonna have to experiment with the torch kerf width and the gap, the uncut portion. There's probably gonna be an issue cutting long sections of tube with multiple bends in that there's not a lot of structure left on the tube to hold the remaining section. So after several cuts in a long tube, it may twist or these gaps may bind in the bearings. But we'll bend this up. I'll put it in a small jig, put some tacks in and just see if we get 90 degrees, if the ends are the correct length. And then if that works, then we should be able to make some bigger tests. Just before I tack, there is a gap between each of the slots that's going to be difficult to avoid as long as one part is connected on the outer edge. There's always going to be a gap, so I'll think about that. I don't know if that's going to be an issue for welding, but we'll tack this up and then we'll see. Here's the test piece. It's not quite 90, the jig slipped a little bit, so the only concern I have is because they're still connected by the bridge that there's this fret gap, which I might be able to perforate and then close the spacing. Ignore the terrible welds. But this bend radius can be anything that you want, and it will provide for routing of tubes, exhausts that the CNC tube bender can't do. The tube bender can only do certain bend radius. So this is good first test. I'll take some measurements and just make sure that the calculations for generating the G-code to cut these parts are correct. Check with the welder just to see what they think about the gap, because that's not the greatest. That's a consequence of leaving the bridge that keeps them all connected. So the benefit of this is that you can design in software a exhaust routing that you want. Cut the part, just bend it like a slinky, tack it, weld it in, rather than messing with a bunch of different parts.